quick visual recap. We know that planets obey Kepler's laws, and that, as Newton showed, comes from the 1 over r squared force, and that is not the 1 over the square root of r of Don's filament model. On the other hand, we know that planets obey this spacing, and it's this formula that doesn't come from the 1 over r squared, but you'll notice this minimum radius term followed by this nice geometrical pattern. That's what we see in Don's model. If this is the axis of one of Don's filaments, we have a minimum radius where the magnetic field is axial, and then that nice geometric spiraling after that of spiraling rates. So here's the insight. What happens if, remember, the reason we got this is that's the minimum energy configuration, which means that planets have to be following the magnetic field lines of one of Donald Scott's filaments, okay? So what happens if we try to match the inverse square law, that is, we say that planets are bound to the sun by some inverse square force, but they also follow in the minimum energy configuration of a filament. And that's where we're going to get this relationship of eccentricity to inclination of orbits. And here's how it works. Let's start with the simplest possible gravitational orbit. That's a circular orbit of a planet around the sun, a constant radius, and a constant winding rate. So can we match that to Don's filament? Yes. All we have to do is say the sun is traveling down the filament and a planet is wandering at a constant radius at a constant winding rate. That's a circular orbit and a nice helical orbit in Don's model. But notice that means that the planet orbits in a plane traveling with the sun. From the sun's perspective, it travels in a plane around the filament like that. But can we put a planet in a gravitational elliptical orbit where it's closer to the sun here and farther from the sun there, and traveling faster around the sun here and slower around the sun? Yes, that works in the gravity-only model. And it also works in Donald Scott's filament, but here's the thing. If the sun is traveling down a filament and a planet wanders in or out radially, that changes the winding rate, and that changes both the azimuthal component as far as how fast the planet circles the sun, but we need that in this model, and it also changes the axial component of how fast the planet races ahead of the sun. So now here's where we compare the two orbits, a circular one compared to an elliptical one. The circular one stays in this plane like that. The planet that wanders in or out must go out to where maybe it's more axial and race ahead. And then on the other side, where it's more azimuthal, it goes around the filament as opposed to down the filament, and you end up with circular orbits like this, or elliptical orbits inclined like that.